So we were talking about steady state conduction. Okay. You know what is a steady state conduction? Which term do you ignore in diffusion equation? This is what? That is the storage term, right? So you ignore that term in steady state, right? We were talking about a particular case where we could represent thermal resistance, okay, and this is basically synonymous to or analogous to Ohm's law, basically this kind of derivation. And we were at a point where we came up with this solution that R thermal, especially for R conduction, to be more appropriate, that was equal to what? L was the wall thickness, this K is thermal conductivity, and this area is the cross section area. Okay, we were at this point, and if you remember, we derived this thing. Okay, I would start from this one. We talked about derivation of temperature profile. If you have 1D conduction in an infinite wall, right? And if you remember, we have one isothermal wall here, the other isothermal wall here, and you can derive the temperature profile if you have, let's say, some insulation or some flux boundary condition over some wall. You can derive it, right? And we also derived this equation for this Q generation term. Okay, if you have that, then temperature profile would become quadratic. If you don't have any generation term, temperature profile would be linear. So just to generalize this thing, this is you can say a note in the ongoing discussion. If you have a varying cross sectional area along the length, then what would you do? Till this time we have been talking about those walls where we have constant cross sectional area, right? Constant cross sectional area, that is not going to change. But at some point you may have varying cross sectional area. Like if you go in this direction, you can see that the cross sectional area is varying, right? So in that case, what you can see is, what is the relation for Q dot? That is equal to Ka dt by dx. You remember that? Now, can you represent this area as a function of x? Area is varying as long as you are going in x direction, isn't it? So area is a function of x. So what you can write is, from this relationship, I would write this thing, Q dot 1 over A dx equals K dt. Can I write this thing? Okay, and then you can integrate it. Now, how to represent this area as a function of this x? You know it from your calculus course. You should know it, right? So this is the relationship. If you have constant heat flux, varying cross sectional area along the length, and K may be a function of temperature. Thermal conductivity may be a function of temperature as well. Okay, so if you have those kind of relationships, you should use this one. And remember the assumptions or the limitation. This is only true for steady state, not for, by the way, Yes, you can say it is not steady state. We are talking about this constant heat flux. Yes, it represents the steady state case. Okay, it is not going to vary with respect to time. So then you can manage these kind of conductions. Okay, remember this one. Now how to integrate it, you know, but much better than me. Okay, so the only thing is you should be able to represent area as a function of x and K as a function of temperature. So then it's a simple problem of integration. Okay, now this is more important one. We are going to talk about this radial system. Radial system means, why do you need to have those kind of radial systems? Because you need to design, let's say, wires for electrical conduction. You need to design pipes for, let's say, transferring one fluid or gas or steam from one point to the other. It may also be used for oils as well. Okay, so you need to be very careful about the heat transfer. Okay, now this is just a representation of a pipe. You can see that inside that pipe there would be a hollow portion from where the fluid would pass. Then you have a layer of material, and through this layer of material you would have what kind of heat transfer? Conduction. Outside that layer you would have convection. Why? Because there may be water, there may be air. Okay, so for example, if I want to write down, let's say I want to make this thermal circuit for this problem. Let's say there is convection. Why? Because there would be a fluid inside it, isn't it? Just be very careful. There would be a fluid inside this hollow portion, and obviously between this side of the cylinder and this fluid there would be convection, isn't it? Why? Because the fluid is moving, so there would be convection. Then in this portion, in the solid portion, you would have conduction, and then finally at the outer portion you would be having convection again. Okay, so just look at it. If I want to draw the thermal circuit, this is the innermost temperature. Let's say this temperature is T infinity 1. I can develop a node over there with temperature T infinity 1, and then this resistance would be what kind of resistance? Convective resistance. This would be convective resistance, and then again this solid material, which is what? A conductive resistance. Okay, let's say this may be the temperature at this point. Sorry, this point. Let's say this is TS1, and then at this point you may have temperature TS2. I'm sorry, I'm not following the convention notations which are given in this figure, but I'm just trying to make this thermal circuit. Okay, and then finally at the end you would have an other convective resistance, and on this node you would be having T infinity 2. Okay, is there any problem in developing this kind of thermal circuit? You just need to identify whether there is convection or conduction. That's it. Okay, so you can see that inside the pipe, between the inner fluid and the inner surface of the pipe, there would be convection. Okay, fine, then there is a convective resistance. Then from this side to this side, pipe has solid material, so then it would be what? Conductive resistance. And then outside surface, at the outside surface you would have convection again. Okay, so now the problem is you can't use those relationships which have been derived for Cartesian form of the thermal resistance. Cartesian form, right? In Cartesian form or plane walls, you would have R equals L over Ka, and that was derived from where? If you remember, we derived it from one-dimensional steady state without any heat generation, heat diffusion equation. You remember that? We derived that R thermal conduction by using few assumptions: steady state and no heat generation, and what? 1D, right? So the same we can do for radial pipes as well. Like for example, if you go to the radial pipe, if you look at the cross section, major heat transfer would occur in radial direction. In case of pipes, major heat transfer in what direction? Radial direction. Okay, so we would be only interested in the term which is basically d something by dr of the cylindrical coordinate form. You remember that? I wrote down that equation. So what would be the term? Can you look at your notes and tell me what was the term? 1 over r what is that sigma? Okay, that is partial by partial r, then again bracket, okay, okay, and that would become, yes, we are talking about steady state. If we are looking into the thermal circuit form, we need to take the process as the steady state one. Okay, and generally we encounter with those kind of cases generally. So this is the equation. Okay, now if this is the equation, you can see that this term needs to be 0. Why? Because 1 over r would not be equal to 0, isn't it? So this term needs to be 0. So if this term needs to be 0, it means partial T by partial R, this partial T by partial, if I open this term, you would have KR partial square T by partial R square, and let's say, or I can say partial by partial R KR partial T by partial R. If I open this term, I can write this thing from differentiation principles. You understand that? Now, if you look at this thing, if I say that this term is 0, if I say that the derivative of this term with respect to r is 0, what does that mean? That this term is not a function of r, isn't it? This whole term is not a function of r, and basically whenever you have partial T by partial r term over there, it represents what? It's a measure of q dot. It's a measure of q dot. Now it means that by looking at this term, I can safely say that q dot would be a constant term. It would not vary when you change r. Okay, I repeat, if you have this term derivative equal to 0, this partial T by partial r is a measure of q dot. If this is not going to be disturbed with respect to r, it means this is not going to be disturbed with respect to r. It would have no dependence on r, right? So if it has no dependence on r, it means this is a constant term. You understand that? Now, Fourier law says that q dot, that Fourier law in cylindrical form says, okay, Fourier law says that this q dot would be equal to what? That should be equal to minus k cross sectional area into dt by dr, right? This is the Fourier form. Can you understand that? This is the Fourier form, right? Now, what would be this area? Perpendicular to the direction of heat transfer. Now, if you talk about this radial direction, heat is going in this direction, normal to this radial direction. Isn't it the surface area which is basically normal to this heat transfer direction? Just look at it. This is kind of a pipe. Heat is going normal to the normal to each and every point on this surface, isn't it? So this is the surface area which should be used here. Okay, this is the surface area, and that surface area is what? 2 pi RL. Okay, now just look at those few relations. That was the actual term. That was the actual term which we used to conclude this thing to be as a constant, right? And then QR from this term, this is from Fourier law, you can write it down. And this is the area which should be used over there. Which area? Which is normal to the. Okay, so that area needs to be what? The surface area, right? So this is the Fourier law form for cylindrical coordinates, right? Now, by solving this equation, you would get this temperature profile. What was the term? That was 1 by R, partial by partial R, what? KR partial T by partial R equals 0. I hope you can solve it, right? So finally you can have temperature profile as natural log of R plus C1. Sorry, C1 natural log of R plus C2, right? Now just solve it. It's a very simple equation. You can solve it, right? Now the C1 natural log of R plus C2. Now you see that for radial system the temperature profile is not going to be linear. It is what? Logarithmic. It is what? Logarithmic, right? Now these two coefficients can be calculated by boundary conditions. And it depends whether you have an isothermal surface on one side or let's say some adiabatic surface on the other side. So it depends, okay? But anyways, you can calculate it. I have shown you one example in the last class, if you remember. I calculated those temperature profiles for both of the Dirichlet and the Neumann conditions, okay? So let me go back to this slide. Do you have some question? Theta and the Z direction. Okay, fine. Now, if you have, you remember from fluid dynamics we talked about some kind of swirling or some kind of, let's say, hydrodynamically stable region. You remember that? And then you have some kind of thermally stable region. Okay. So the point is that if you talk about some fluid flow in a pipe, you talk about those portions of the pipe as far as those computations are concerned. I'm not talking about the experiments and all that stuff. I'm talking about the computation or analytical solution. Okay, as long as you are talking about the analytical solution, you only talk about in those regions where you have major fluid flow in one direction. You remember that we talked about hydrodynamically entrance region, and then there is a region which is hydrodynamically stable region. Okay. So what you see is that if there is no swirling at all, you can't expect that there would be some kind of heat transfer. Obviously there would be some heat transfer, but that heat transfer would be minimal. In theta direction, let's say this is the one fluid layer and this is the other fluid layer in theta direction. So there should be some heat transfer, isn't it? But if the flow is going in this direction, you would say that okay, fine, that heat transfer is very minimum. You understand that? And as far as Z direction is concerned, in Z direction you assume that the let's say again in comparison, not specifically but in comparison to heat transfer in the radial direction, you say that this heat transfer is again minimum. Okay, so this is just, you can say, a comparative statement. In real situation you don't have those two theta term and let's say the Z term, you don't put it equal to 0. In comparison to the radial term, they are minimum. Okay, that is the point. Right, now you have this thing. you have this thing. Okay. Now my point is, if you put the boundary conditions over there, you can calculate C1 and C2. Just assume that you have these two boundary conditions. Let's say TS1 on this surface and TS1 on this surface and TS2 on the inner surface. If you plug those two boundary conditions in this relation, you would come up with this expression, right? Do you understand that? Come on, if you don't understand it, just ask question. I repeat. What did you have? C1 natural log of R plus C2. So at R equals Ri, let's say, or R1, you had what? T equals TS1. At R equals R2, you had T equals TS2. Can you plug those two conditions over there? Finally, you would come up with this one. Okay, why? Because QR is constant. Okay, is the problem resolved? Any question? Okay, so you come up with this thing, QR equals, I'm sorry, this QR is equal to 2 pi Lk TS1 minus TS2, and then we would have natural log of what? R2 by R1. Yes, R2 by R1. Now see, this is what? This is just like voltage difference. This is what? This is just like current. So rest of the thing is 1 over R convection in case of radial systems, piping systems, okay, wiring systems. So you can say that R radial would be equal to natural log of R2 by R1 over 2 pi You understand that? So this is the point which I want to emphasize, that if you are talking about a plane wall, you know what is the thermal resistance. It is very easily understood. Okay, L by Ka. If you have a radial system, the form of the thermal resistance would change. Now it is dependent on some log of R2 by R1, right, and divided by some part of the surface area, and then you have K over there as well. Just see, that was L over Ka. See, instead of A you have this thing, instead of K is already there, and instead of L you have some dependence on radius. Sorry? 2 pi L what? No, it is just a measure of area. Like what is surface area of a pipe? It would be 2 pi R2 into L, isn't it? 2 pi capital R into L. So that R has been counted over there. Okay, just do the calculation, derivation, and you would see how it goes over there. Okay, so this is 2 pi Lk, and it is being divided by natural log of R2 by R1, and then you would have R radial. Do you understand that? Okay. Sorry? No, it depends. It depends. Remember, those forms of, let's say, thermal resistances have been derived for isothermal boundary conditions. Remember that, isothermal. I only considered temperatures on those two boundary conditions. Right? So this is an interesting problem, that if you take some adiabatic surface over there if you take some adiabatic surface over there and you see what would be the thermal resistance. By the way, I talked about this thing in the last lecture, if you remember. You should remember it. You remember I solved this problem when you have this T1 over there and dt by dx at the other side, which is equal to 0. So what was the temperature profile at that time? That was a simple constant temperature profile. The temperature profile was not changing, and by looking at the physics I can say that if I have some other temperature other than this T1 on this side and it is an adiabatic surface, heat would have no place to go once it reaches this wall. Okay, so it means this is basically physically impossible to have this kind of boundary condition. dt by dx equals 0 at some point, and then on the other side you have temperature. Okay, so please look at these two conditions, but my point is we have derived this thing for two isothermal sides of a pipe, of a plane wall, and similarly you can see those relationships for sphere as well. So this is your reading assignment. You can see the sphere case in your book. Okay. Now there is a very interesting problem. For example, if you look at a plane wall and you start putting more and more insulation on that wall, let's say I repeat my sentence, you start putting more and more insulation on that wall. What you are trying to do? You are trying to minimize the heat transfer rate, isn't it? If you put more insulation, you try to minimize what? Heat transfer. Now see, if you have a cylindrical wall, let's say a cylindrical, not wall, you can say cylindrical pipe, and you are basically transferring some fluid from one point to the other. Let's say it is steam, right? You can't have ideal insulation, you know that. All the insulations would have some value for K. It can't be 0. Some value of K would be there. It means some heat would be lost in any case. Now for example, if this is a pipe, you have some fluid going through it, and you put more and more insulation on that pipe so that no heat transfer can be carried out from fluid to the air, let's say. Now my point is, if you increase the thickness, as far as conduction is concerned, your thermal resistance would increase. If you increase the thickness of the insulation, I repeat, if you increase the thickness of the insulation, your thermal resistance would increase. You understand that? And you can say that the heat conduction would decrease as far as conduction is concerned. But at the next level, if you are increasing this insulation, it means you are increasing the radius of the pipe. Do you understand that? You are putting more insulation on the pipe, so it means you are increasing the radius of the pipe. If the radius of the pipe is increased, surface area of the pipe would also increase. But that increase in surface area would increase convective heat transfer. You understand that? Putting more insulation on a pipe would decrease conductive heat transfer, but it can increase convective heat transfer. So this is a big problem in, let's say, in pipe designing. If you are talking about, let's say, transfer of fluid from one point to the other, or let's say current passing through a wire. So this is a problem, that what should be the thickness of the insulation, right? So that is why I selected this thing, right, just to discuss it, that this is the critical radius of insulation. What should be the radius of insulation? This is the critical one. Sorry? Okay, I repeat, not the conductive one. I repeat, if you put more and more surface area, if you provide more and more surface area for convection, what would be the effect of greater surface area on the convection? Its heat transfer rate would increase. You understand that? So you can say that the conductive resistance would decrease. Why? Because you have more surface area. You understand that? Now see, look at the cross-sectional area for the conductive heat transfer. You put more insulation. Now conduction is going in this direction. You put more insulation on that. So putting more insulation would decrease conductive heat transfer, isn't it? You would not understand that. If you put more insulation, you can't understand that it would reduce the heat transfer rate. Can you understand that? If it reduces the heat transfer rate, it should obviously increase conductive resistance. Simple as that, right? So it's other way around. They are inversely proportional to each other. So my point is, for piping system, it becomes a critical problem. For piping system, it becomes a critical problem. Why? Because your pipelines may go through that, let's say, atmospheric boundary layer where you have air, or let's say it can go through, let's say, some sea or some river. So you would have conduction and convection simultaneously happened over there. So the point is, what should be the optimal thickness? The point is, what should be the optimal thickness, and how you would select that optimal thickness for different types of applications. This is the point which I want to talk about. So just look at that. Adding more insulation to a wall always decreases heat transfer. Why? Because it would increase the thermal resistance. The thicker the insulation, the lower the heat transfer rate. Yes, we agree. Adding insulation to a circular pipe or spherical shell, however, is a different matter. Now, why it is a different matter? I told you that adding more insulation on a pipe would increase what? Convective heat transfer rate, but it would decrease the conductive heat transfer rate. So you should have some kind of compromise between those two. So I want to solve this problem. Okay, I want to solve this problem. Just look at it. Let's say this is the cross-sectional area of a pipe. This is the cross-sectional area of a pipe. This is the inner radius R1 and this is the outer radius R2. Some kind of fluid is going through this pipe and this is the hollow section. And this portion, this gray portion, is the insulation part. Okay, this gray portion is the insulation part. Now see, you understand this system? Is there any problem? Outside this insulation there is convection, isn't it? There would be some kind of H, there would be some kind of T infinity, right? Now I assume that the inner surface would have a temperature of T1, outer surface may have a temperature of, let's say, T2, and this is basically T infinity. Why? Because if you talk about this is conduction. If you talk about heat transfer from the outer surface, this is convection. Now see, these are the thermal resistances for both of these heat transfer phenomena. This one is, let me draw it over there just to clarify this thing. We have this pipe. For this conduction I have this resistance. For next one I have convection. On this side I have temperature T1, on this surface I have temperature T2, and in the surrounding we have temperature T infinity. So this would be T1, this would be T2, and this would be T infinity. You understand that? Now what is R total? R insulation plus R convection. Do you understand that? Right? Sorry? No, we are not talking about that one. Although we can include that as well. But the problem is comparison between conduction. What is the original problem? Just look at that. Concentrate on that one. That is basically conductive and the convective which is happening outside. Okay, this is what is dominant. You understand that? So this is R total. Now what would be R total? By the way, this is a radial system, so what would be R insulation in that case? What was that? Come on, natural log of R2 by R1 divided by, and what is R convection? If you remember, 1 by HA, we derived it in the last lecture. So that would be what? 2 pi R2 into L. Oh, sorry, this is H as well. You understand that? So now this is R total. Now because I do not know, I know this R1, I know this R1, but I still need to select this R. So I would not put R2 over there, I would simply use R. You understand that? Now this is total thermal resistance. My problem is I want to find out the minimum thickness. I want to find out the optimum, I would not use the word minimum, I would use the word optimum. Let's say I want to find out optimum thickness. Now if you remember from your calculus course, do you remember how do you find out minima or maxima of some parameter? You remember that? If I want to find out optimum, for example, I want to reduce this parameter. Let's say my problem is I want to minimize this parameter, and this parameter is a function of R. So if I want to find out the minima of this parameter, what I can say, I would take derivative of this R total with respect to R and I would put it equal to 0. Do you understand that? Very simple. Okay. Now I would simply write down the derivation and then I would talk about the physics. Okay. If you take this derivative, that derivative comes out to be 1 over 2 pi kr plus 1 over 2 pi r square h equals 0. This is the derivative of that R total term. You have two terms over there, you can derive it yourself, differentiate it yourself, and from here you would find that R would be equal to K by H. So this is the radius at which you would have optimum R total. Okay, this is the radius. And if you want to find out whether it is this R equals K by H provides you the minimum R total or maximum R total, you need to take what? Sorry? By the way, those two quantities should be positive. Okay, both K and H are positive. Just look at the derivation. If you have any problem, come to me again, right? So what was the point? That optimum R total can be minima and it can be maxima. You remember that from your calculus? So you need to perform what? Second derivative test. Okay, you need to perform second derivative test. So if I take this thing at R equals K by H, if I take this thing at R equals K by H, that comes out to be 1 over 2 pi K cube over H square. Okay, and would this term be positive or negative? This term would be positive. So it means this was what? If second derivative test, it comes out to be positive, you would have a minima at that point. If it comes out to be negative, you would have a maxima. Okay. So now it means by looking at this discussion, I can say that if I plot R total with respect to R, I would have this kind of plot, and on this R critical equals K by H, I would have minimum R total. I can say this thing. Okay. Sorry? R total what? No, R total is minimum. It means heat transfer rate is maximum. No, it depends on the application. It depends on the application. For example, I would take two cases and I would tell you what is the implication of this relationship or this result. Case 1, you are talking about design of an electrical wire, let's say. Now in electrical wire, you have current passing through it and then you have some portion of insulation, and that insulation basically tries to save the user from the electrical shock, right? But that insulation should provide enough resistance so that all the heat generated within that wire can be transferred in the surrounding, so that that wire could not be burnt out. You understand that? So in that case, if you increase insulation, I repeat, if you increase the insulation thickness, you should have what? Your thermal resistance should decrease. You understand that? If you increase the insulation thickness, your thermal resistance should decrease so that you can have maximum heat transfer, right? And this happens on this side. If you look at this portion, you increase R, your thermal resistance would decrease. You understand that? Now see, there is case 2. If I want to design a pipe to transfer steam, let's say, obviously you don't want to let's say incorporate anything which reduces the steam temperature, right? If you put that steam into the pipe from one side, you obviously want that steam with minimum heat transfer should be carried out to the other end. So it means if you increase the insulation, that R total should increase, isn't it? For minimum heat transfer, you should increase what? R total. Your thermal resistance should increase. It means you should go on this side. So you calculate your critical radius and then you keep on increasing it. And obviously, where would you end? It depends on the cost and the material. Obviously, there are other considerations. But as long as you are talking about the heat transfer, this side is for electrical wires and this side is for pipes. Do you understand that? If you want to design an electrical wire, you want your thermal resistance to be minimum or maximum? Minimum, so that the heat generated within that electrical wire should be transferred outside. So what does that mean? That thermal resistance should be minimum, but you need to put certain amount of insulation on that just to save yourself from the electrical shock, right? So it means if you increase the thermal resistance, if you increase the radius, if you go from this side to this side, you are increasing the radius, isn't it? You increase the radius, but still you are on this side of this critical radius, on the left of the critical radius. So if you are on the left, does not matter how you increase the thickness, how you increase the insulation radius, your R total would be decreasing. But if you want to transfer fluid from one point to the other without any kind of heat transfer, you should look at this side, right side of that R critical. And here you should do what? You should increase the radius if you want to have some kind of heat transfer from the pipe to the surrounding. But if you want to suppress it, you need to be on the right hand side. Okay, I think I have spelled it correctly. There is no inverse or direct proportional relations missing over there. But anyways, any question? So it is quite interesting, and it is, by the way, just you can see where you can use these concepts in actual systems. Okay, so I would stop at this point and we would be talking about fins in the next class, extended surfaces.